Okay, this is chapter 14 of the lecture notes that is about ecosystems. So what ecosystems handle is they have different kind of species. Usually the simplest case is the fact that we have one predator and a prey, right? Here you see that an example can be a bird and a worm. And this, of course, is nowhere near the complexity of the real ecosystem in the world, but we always kind of start from the simple and kind of reproduce the behavior we observe in nature and kind of complicate our model from that perspective. So from that philosophy, it's very good to just start with a simple model that we only have a predator and a prey, right? So what is the simplest mathematical approach that we can move? Is we assume that we have a predator, that is one species that is hunting a prey, right? So the idea here is that what happens to the population? This is what we are interested in. What happens to the total number of preys that are alive and total number of predators that are alive? Normally, in these kind of cases, of course, these guys depend on this, right? These feed from, let's say, leopards feed from antelopes, right? But what do they feed from? Grass, right? Or trees. So in this case, just to reduce complexity, we kind of assume that these don't depend on the resources. So we just assume that there is enough grass or enough trees or whatever they eat, fruits, that there is enough of the resources that they don't need to worry about the food that they're going to receive. If we make this assumption, the problem becomes very simple, because here we kind of associate the growth of each species with a differential equation. So X here refers to prey, right? What do? They kind of increase their population, right, over time, which is the reproduction. What is the reproduction proportional to? Their population, right? The more antelopes there will be around, the more they will mate, the more they will reproduce. So that's why the growth term here is proportional to their population X, and here alpha is the growth rate for preys, right? And then of course their population will also decrease. There will be a what is the reason for the decrease? It's not the competition, because we don't have any competition for preys. We assume that there is enough resources. So this term here is proportional to hunting events, which is a leopard hunting an antelope, which we assume on the very simplest level. We say that the hunting events are proportional to both number of antelopes and leopards. If there are more leopards, there will be more hunting. If there are more antelopes, also there will be more hunting. And of course, this is another coefficient we kind of place here. Is this clear? Okay. And then we have the equation for the predators, right? Here, unlike the other one, here, if we had more antelopes, they will grow more, right? Here, we have the opposite behavior. If you have more leopards, they will grow less because there is a fierce competition, right? So if there are more leopards, they won't be able to hunt as much. So they will be, or per leopard. So this is kind of a term for introducing a competition in the differential equation. And here we have a term again for hunting, because the more they can hunt, the more they will be able to grow. Is this clear? The simplest model. What will happen in this kind of model is that the output behavior of the population of X and Y is going to oscillate. What is the fundamental reason or the explanation for this? Is that you see that the number of preys are very high in the beginning. The orange ones here are predators. So what will happen is that when there is plenty of antelopes all around, leopards will be very happy. They will keep hunting, keep reproducing, they will grow. Until it will come to a point, the number of antelopes will really drop. In this case, there's not a lot of antelopes around. They will start starving the leopards. They won't be getting enough per leopard. enough food, and then their starvation will reduce the hunting significantly. In this case, the antelopes will start growing again. Okay, this is a differential equation that results in oscillations. Actually, it's quite possible to, it's included in the lecture notes. You convert this into a kind of harmonic oscillator equations with kind of change of variables. So here, what we can look here is that what are these kind of here. This is like a phase or configuration space representation, and these arrows indicate where are the populations going. For example, here you see that if I am in this point, I have this x value of prey and this value of predators, number of prey will increase. Or if I am here, for example, it will increase more the number of predators. So I am going to be rotating around kind of this map. And here you can also see that, of course, here what we can also see is that there is a stable equilibrium point that is here for these kind of parameters. If we get these ratios between the parameters I introduced in the first slide, I get kind of an equilibrium population. The further away I start from the equilibrium population, the stronger the fluctuations are going to be, higher the chances of extinction for a population. Of course, here we don't have any parameters that are stochastic, right, for this model. You can always introduce some random terms in these equations that will create stochasticity. Whenever you have stochasticity, you will have the probability of extinction for the species. For example, if you run this simulation, it will never reach zero, this number, because it's a periodic function. And if we keep simulating this forever, they will oscillate, these two species. But if we had a random term, it might add some noise to the output, and at some point it could come to a point that a predator could become extinct. It could happen the same with the prey. If the predators increase too much. However, there is one difference between the output behavior. If prey get extinct, predators also get extinct over time with this simplest model. But if predators get extinct, prey don't necessarily need to become extinct, because they don't need predators to keep living. Okay, and then you can see that not only this, we have this equilibrium point, but also we have a variable that is called an invariant of the system, which is this function of x and y. Why is this an invariant? We kind of take if we assume these like force fields, we kind of get the equipotential lines of this system of x and y, and this can be calculated like this, and you can kind of take the time derivative of this function. You kind of, how do you take the time derivative? This will be delta dx dt. This will be, for example, gamma divided by x dx dt, blah, 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 all the terms, and kind of replace dx dt and dy dt from the initial equation back into the equation here. You will observe that this equation will be zero. The derivative of this will be zero. So this is why this is called an invariant. So what this implies is that theoretically, wherever I start on this chart here in my population, initial conditions of my populations, if I start here, I will keep oscillating on this kind of curve. Is this clear? So you see that some of them are not stable. For example, if I start here, they kind of become extinct, right? So not every starting point is really stable forever. So some of the numbers will end up totally diminishing the other species. So it's like there is an allowed zone. This is important. Is this clear? Also, this extinction probability over time, if we have noise, is going to overall increase as we get away from the equilibrium point. You see that if I start here, the oscillations will be very small. They will kind of just keep oscillating around the equilibrium point with very small numbers. Is the simplest model clear? We'll just check if I'm, yeah, okay. And then we come to the point how we can simulate this, right? Of course, the simplest way is just like we did in the molecular dynamics case, we apply the Euler algorithm. We have at each time step the number of prey and the predator, right? We put this into the equation and we kind of course, this is the, like, this is the previous equation was here, that was the time derivative. So if I put xn here and divide by delta t, this part will give me the derivative. And these are the terms that represent the derivative of each component, right? I can get the terms here like this, which is at time step n. I put every term in the equation, I calculate the next point. Here I have an error that is associated, an integration error that is associated with the finite delta t that I'm using in my simulations. And this error is going to increase as I increase delta t, right? As always. Is this clear? So the more delta t I put in my equation, the more deviations I will have at the end, okay? This number, and we can see that here is that the number of predators at the end of each loop is going to decrease. Can you see it? It's not level. This is not conserving. And also here, according to my differential equations initial model, this variable, the invariant that I was showing you here, this value here, is not conserved over time, which means that the simulation is not stable. If I run this long enough, it will kind of becoming extinct for one of the species. It's diverging. Of course, another strategy can be that if I can make the simulation in a way that I consider the next time step when I calculate it. So when I calculate the derivative here, I also take into account the end point. And here, of course, this is not very direct, because what we have to do is that we can kind of put these points here, xn plus 1, yn plus 1, but here also another term yn plus 1. So we have to take these terms to the other side and kind of solve these two equations for xn plus 1 and yn plus 1, because there are these terms on this side as well. But it's a simple algebra. You can do it on your own. And there is also a hint in one of the exercise boxes that shows you, gives you the explicit formula if you are lazy to calculate it, okay? And here what will happen is the opposite. It will go in the other direction, that the population will increase and increase and increase. So again, we end up in a kind of a unstable solution numerically. Of course, this really depends on your delta t, choice of your delta t. If your delta t is very small, you may not need to care about this, okay? It's not, but really, like this time scale that is decreasing over time depends strongly on choice of your delta t. If you decrease it to, for example, delta t by 10 times, maybe you increase the number of simulation run for this to diverge this much, maybe by about 100 or 1,000 times. So it's really dramatically dependent on the time step we choose here. Okay, and then we have this symplectic Euler integration. So here what we do is that we kind of wait a second, the one on the right is wrong. No, it's not wrong. Okay, so we can apply this in two different ways. What we do is that when we calculate the next point, we take, for example, the current point for prey and the next point for predators, or we can do vice versa. We can take the next point for prey and the current point for predators, kind of. This kind of gives an approach that is very similar to what we explained as leapfrog algorithm in the first lecture. So this is for for the case of multiple variables, we kind of take one. So in these kind of integrations, in Euler integrations, what we do is simply this, right? We take this area, right? I mean, the simplest one-dimensional integral. If I take this value and multiply by the width, I underestimate the area, right? This remaining area is not calculated, which is not right. Of course, this error really proportional to at least the square of my time delta t. And here, if I take this point at the end, I overestimate the integration, right? So for two-dimensional differential equations, this is a nice trick that we kind of take the beginning point for one variable and the end point for the other variable. And you can do this either way. You end up having a much more stable, numerically stable simulation. So this plot is not only important for simulating predator and prey. If you have two variables that counterplay in any simulation, and you want to kind of implement an integration algorithm, you have kind of a dependency that you can model with a differential equation. In this case, it's very useful to use these kind of either one of these approaches, whatever is simplest, or you can kind of try both of them. It's not always the same. For this particular differential equation model, they're absolutely the same. I mean, in terms of stability, they give you equally good stability. But for different simulations, especially if you have multiple species, it might give you different stability. So you need to really try and see which one works best. But it's a very useful method. It's called symplectic Euler integration. Okay. Is this clear how to implement this? So we take only for one variable the next step. It can be the predator or the prey, and the current variable for the other, the current step for the other variable. And in this case, we will observe that this will keep oscillating and oscillating on the same kind of curve. It will be very stable, and it will be conserving its invariant. Is this clear so far? Do you have a question? You don't understand anything?
No. I'm just wondering if it be applied here as well.
Which one?
On both equations.
Mm-hmm. Let me see here. Gamma x. You're right. This should be y, right? Because this is the prey. This is the hunting event. This is the competition. Gamma. Now this is a good point to, let me just see again. Yes, gamma y, and that should be y. Yeah, thank you for noticing that. It's a mistake, so we need to correct it. It's good to, I will just quickly take a note of that. Chapter, is it chapter 14? 14. Okay. Okay, great. Perfect. Thank you for noticing that. Yeah, I didn't notice that, but yeah, this is written wrong. Obviously, this should not depend on minus. This should be, this is the competition term that is decreasing the population of prey. It should be y, as in the initial equation. Okay, and another kind of way to model this kind of behavior with different species is it's called logistic growth model. Here, we don't assume that we have multiple species, but we just assume that there is a capacity. So there is kind of our environment, right? For example, for horses, this can be fields that are available. For fish, this can be the amount of resources or space in the ocean. or for trees, this can be like the physical space that each tree needs to grow in a forest, right? For this can be anything. So here we have two terms here. Again, we have a growth term, right? Here, so my growth in population is proportional to population. This is easy to understand. It's reproduction. The more trees there are, the more they can grow next year. And of course, we have another term here that is the decay in growth due to the capacity of the environment. And here the capacity of the environment for this kind of an equation is represented by the ratio of these two terms. The term comes with x and x squared. Okay. And you can, of course, also represent this with this kind of behavior, so that we kind of take into parentheses and we substitute this variable to remove alpha here. So we kind of get into this equation. So we have a growth that is proportional to x, but also proportional to 1 minus x divided by the capacity. So as x is approaching to the capacity, this term is going to approach 0, which means that the population, the growth of the population, is going to decrease. Is this clear? And of course, you can always do the math. What is the population here for this equation that gives me the maximum reproduction? What is that value? We are going to maximize this number, right? X 1 minus x divided by kappa. If you want, when does this happen? K divided by 2, right? Why is this important? Why do we care so much about this? Because it's sometimes that's something we are farming, right? It could be that we might have a farm of fish. We might have a farm of sheep. We might have whatever farm we have, right? Trees. We are planting tomatoes, right? If the farm is overpopulated, that each tomato don't have enough space to be able to reproduce fast enough, right? The reproduction rate is slow due to the fact that we are close to the maximum capacity of the population, then the production rate will decrease. So this is an important parameter in the model that we can actually try to optimize. So also people that fish, this is most important actually is very a common kind of dilemma for people who fish often, because they don't really know the number of fish in the ocean or in the sea, right? But they try to keep it at an optimum level, because if they don't fish a lot, they will reach a certain population and they won't increase further. So they want to optimize the reproduction of the fish over time so that each year they can get more fish, right? But if they overfish, if they estimate this number wrong and overfish, what will happen in that case? The number of fish will go very low. So let's say it could be anything. It could be tuna, it could be salmon, whatever. The number of fish will be very underpopulated. What this means is that the X is very small. It doesn't only depend on this, it also depends on X itself. So if the population is very low, the reproduction for the next year or for the next season is going to also decrease. So this is very important for example, people. Why is it more important for people that fish? It's more difficult to estimate or measure the population of the fish in the ocean than if you have a farm of sheep, or if you are growing tomatoes in your garden. It's very easy to count how many trees or plants you have, right? But if you have farming fish that you don't really know the number, it becomes more and more critical that to estimate the number correctly. Otherwise, you end up risking, for example, overfishing or underfishing in a way that you don't optimize the reproduction. And here you see a solution of this equation as a function of time, and we start from a very low population. Here we see that the the population is increasing kind of exponentially, which it would do if we didn't have this term, right? Is this clear? Yeah. And what happens is that at some point it will kind of start decreasing the growth rate due to the fact that we are approaching the capacity of the population. And here what we see is that importantly, this model has a good advantage of here the green dots and the blue lines are the same simulations that are done with different time steps. And the green dots are, for the green dots, the time steps are 10 times larger than the blue lines. And here what we observe is that we don't really see much of a difference or a diverging or a converging behavior that is like ruining the fundamental qualitative results of our simulations. So we are not really concerned a lot with the time, the value of the time step that we are choosing to simulate the system. Is this clear? So it's a lot more flexible if you compare it with the other model that I introduced before. And here you can see also that this is a theoretical solution of the equation. So of course here the blue line, they are not overlapped, but if you take my word for it, blue line is a much more closer solution. But the green one, although being representing a little bit of error here due to the finite time step value that I choose, it's still okay to get a result like this. At the end, we are simulating things here. And it might, of course, if it's especially considering the fact that this is going to increase my simulation time by a number of 10. Is this clear? Any questions so far on the logistic model? Of course, this is also possible to introduce with noise. For example, for those of you groups, if you have any kind of groups that are making projects or in the future with kind of this kind of logistic models or the prey predator models, you could always use this. You can first you can implement this in two different ways. You can add a noise term to this equation directly, or you can kind of make these coefficients fluctuate randomly around a certain point. Okay, is this clear? So this is another model that we can represent our system. And finally, I would like to mention different things. For example, this is called mutualism. So in this case, the two species become more favorable of increasing their population if the other species also exist in the same environment. Okay. And here is kind of the there are similar behaviors in the that are observed like the original model, but here you see that the equilibrium populations are quite a little bit different. And here you see that, for example, beta 1, 2 represents the like mutualism that the first species feels for the second one. And this one is a strong parameter here. You see the denominator is the same for both of them here. But as this term increases, the equilibrium value for X is particularly increasing, right? But of course, this one is also actually increasing indirectly because it also exists in the denominator. Because if I increase beta 1, 2, this term will decrease, right? This term will increase. Do you see that? Overall, this term will increase a lot. And this term will also increase because although this doesn't change, the denominator will still decrease for Y also, but not as much as this one. So if I increase beta, the mutualism for that the first species feel for the second one, both of the populations will increase, right? But the first one will increase more than the second one. And of course, it's the same way. If I increase the mutualism for the second one, for the second species for the first one, it will end up increasing the populations for both the equilibrium populations, but it will favor more the second species. Of course, here, since we don't have any predators to balance the population, we kind of implement kind of the capacity behavior from the logistic model. If you remember here, this is how we modeled with an x squared term that gives me kind of this capacity behavior, I implement the similar behavior here as well for the mutualism theory, so that we have a term that kind of deals with the overpopulation. Is this clear? And of course, from this point on, you can always make the simulation more and more complicated. So now we have the fundamental models, right? We have a model that what happens when we have a species that is modeled on its own. We have the logistic model. And we have two species, we have the predator-prey model. But we can always complicate these things, these terms more, and you kind of add these terms in the differential equations. For example, this counts for the mutualism between the two species. And for example, this counts for the capacity for X, this counts for the growth, reproduction, right? Sorry?
Besides R2 is supposed to be alpha. Like at X equilibrium, you have alpha 1.
Yeah, I think so. A lot of mistakes. Not good. I will fix it also. Sorry. Where is it? Mutualism. Y equilibrium. Alpha 2. Okay. Yeah, it should be. That obviously should be alpha 2 as well, which is written wrong. Okay, and then the next one is competition. Here you can kind of introduce another kind of set of equations that represents competition between two species. For example, it could be horses and cows that feed from the same grass. We can assume that there is a certain capacity due to the space or the environment, but also these two species compete between each other. Here you see that they kind of have their own growth rates, the both two species. However, when it comes to the capacity, both species count for the capacity for the other one. So you can think of it like they kind of account for the certain kind of capacity proportional to their population. For example, even if they're not competing directly, for example, horses and sheep, if there is a lot of sheep, they might eat more grass or occupy more space. That will eventually inhibit the horses from reproducing more. Is this clear, this formula? So this is, again, you can kind of calculate, do the math, and find what are the equilibrium points for these populations, and do the math for this individual if you have two competing species. And the main idea here is that these are how we kind of model. So if we have multiple species, we put coefficients for each species to the other one, and capacities. For example, of course, the capacities have to be different because the competitors might have different scales, right? For example, even if they eat the same thing, a capacity for cows and rabbits won't be the same in the same kind of an environment, right? An environment as large as Chalmers might host thousands of rabbits, but maybe not as many cows. So the capacities are different, but you kind of account for the somewhat for the other competing species as well. So this is how kind of you generate the model. So here is, in this chapter, we really get the idea of how different kind of species interact. How do they interact if they are mutualist? How they interact if they are competing? How they are interacting if they are predator and prey? How it's the growth of a single species is not affected by any other species, but just the population capacity. So all of these things, we kind of learn how to model them in a kind of differential equation. And from this point on, if we have multiple variables in the equations, which means that we have multiple species, we can always take all of these equations and kind of put these right terms that are that we actually need to represent the competition, the capacity, mutualism, hunting, or reproduction, all of these terms. If you represent all of these terms with this coefficient, of course, the more species you involve, a lot more coefficients that you're going to have to handle. Of course, these things in numerics are always trial and error, and you also constantly keep comparing your results to the real world. How is it in real world? You need to visualize it, see it. Does it look like what we expect to see in a real world behavior? And iterate the parameters and do it again, iterate the parameters until you come to a point that it looks like, okay, this model looks like it's working well and it's modeling accurately what we want to observe. The first thing always is that we get it qualitatively right. And then we start comparing the quantitative behavior, what we observe, what are the numbers we see in nature, what are the numbers we observe in our simulation. Is this clear? Do you have any questions? I think this lecture ends here as well. I remind you once again that the lecture on Friday will be online via the Zoom link, but it will still be recorded and put on YouTube. You know that the playlist to all the lectures is found on Chalmers Canvas homepage, right under the Zoom link. So there is a YouTube link that you can find all these lectures. So if you want to go back and watch one of the lectures, you can go back and check. Okay, and with this, I will conclude this lecture. Thank you very much.